In the world of artificial intelligence, one of the most powerful tools we have today is the transformer, a neural network architecture that has revolutionized how machines understand and generate human language. But beneath the surface of this breakthrough lies a deep, intricate dance of mathematics, attention, and optimization. Today, we're diving into the inner workings of transformers, not just to explain how they work, but to understand why they work so well and where they're headed next. At the heart of every transformer is the self-attention mechanism. This isn't just a clever name. It's the core innovation that allows models to weigh the importance of different parts of a sequence when processing any given word. Think of it this way: when you read a sentence like, "The cat sat on the mat, which was soft," your brain doesn't process each word in isolation. Instead, you instantly connect cat to sat, mat to soft, and which to the object it describes. That's attention in action, and the transformer replicates this with precision. Here's how it works. Each word in the input sequence is first converted into a vector, a numerical representation that captures its semantic meaning. These vectors are then passed through three separate linear transformations to produce three key components: the query, key, and value vectors. The query represents what we're looking for, the current word's perspective. The key represents what's available, the other word's identities. And the value holds the actual content, the meaning we want to retrieve. Now comes the attention computation. For every word, we compute a score between its query and every other word's key. These scores are scaled by the square root of the key dimension, a small but critical detail that prevents gradients from vanishing or exploding during training. Then we apply a softmax function, turning these raw scores into probabilities. The result? A distribution that tells us how much attention to pay to each word in the sequence. Finally, we multiply these attention weights by the corresponding value vectors and sum them up. This produces a new, contextually enriched representation of each word, one that incorporates information from the entire sequence. This is the magic. A single word can now carry the meaning of the whole sentence, dynamically adjusted based on context. But this is only one layer. Transformers stack multiple such layers, typically 12 to 32 in modern models, each refining the representations further. And within each layer, there's a second component, a feed-forward network. This is a simple two-layer neural network that applies nonlinear transformations to the attention output, allowing the model to learn more complex patterns. Now here's where things get even more interesting. The original transformer architecture uses positional encoding to inject information about word order. Since the self-attention mechanism is permutation invariant, meaning it doesn't care about the order of inputs, we need a way to tell the model that cat comes before sat. Positional encoding solves this by adding sinusoidal functions to the word embeddings, creating a unique signal for each position in the sequence. This allows the model to learn relative positions without relying on recurrent structures like LSTMs. But the real breakthrough isn't just in the attention mechanism, it's in the scalability. Because self-attention operates in parallel across all tokens, transformers can process entire sequences at once, unlike recurrent models that must process one token at a time. This parallelization is what makes training large models feasible on modern hardware. GPUs and TPUs can handle thousands of attention computations simultaneously. And that brings us to the next layer, training. Transformers are trained using a masked language modeling objective. In this setup, the model sees a sentence with some words replaced by a special token, for example, "the sat on the mat." It's then tasked with predicting the missing word based on the context. This forces the model to learn deep, contextual representations, not just word frequencies. But modern models go even further. They're trained on massive corpora, hundreds of billions of tokens, using techniques like gradient accumulation, mixed precision training, and data parallelism. The loss function is minimized through stochastic gradient descent, often with adaptive optimizers like AdamW, which adjusts learning rates dynamically across parameters. This allows the model to converge efficiently, even in high-dimensional spaces. Now let's talk about inference. Once trained, the model can generate text by sampling from the output distribution at each step. But here's a crucial detail. The model doesn't just generate one word at a time, it uses autoregressive decoding. That means each new word is conditioned on all previous ones. The process starts with a prompt, and at each step the model predicts the next token, which is then fed back into the input. This continues until a stop token is generated. But this isn't just about generating text. Transformers are used in translation, summarization, code generation, image modeling through vision transformers, and even in scientific discovery, like predicting protein folding with AlphaFold. The architecture is so flexible that it's become the foundation of nearly every large-scale AI system today. Still, the model isn't perfect. It has limitations, especially in handling long sequences. The self-attention mechanism scales quadratically with sequence length, meaning that processing a 10,000-word document requires 100 million attention computations. That's computationally prohibitive. Researchers are tackling this with sparse attention, local attention, and hierarchical architectures, but it remains a major challenge. And then there's the issue of interpretability. While transformers are powerful, they're often seen as black boxes. Understanding why a model made a certain prediction, especially in high-stakes domains like medicine or law, is difficult. Efforts are underway to develop attention visualization tools, layer-wise relevance propagation, and counterfactual explanations, But we're still far from full transparency. Looking ahead, the future of transformers is evolving rapidly. There are hybrid models that combine attention with recurrence or memory networks. There's research into more efficient attention mechanisms like flash attention and mixture of experts. And there's growing interest in using transformers for reinforcement learning, multimodal reasoning, and even general-purpose AI agents. But perhaps the most profound insight is this. The transformer isn't just a tool, it's a paradigm shift. It shows that intelligence doesn't require sequential processing. It shows that context, when properly modeled, can be learned from raw data. And it shows that with enough data and computation, machines can learn to understand language in ways that were once thought impossible. So the next time you see a model generate a poem, translate a novel, or debug a piece of code, remember, behind every word is a web of attention, a cascade of transformations, and a deep mathematical structure that's reshaping the future of AI. This is more than just a neural network. It's a new way of thinking about intelligence, and we're only just beginning.